Now, before we proceed further, we shall start first of all with the practical applications of the structural steel design. So, I presume that you do had, learned enough of the theoretical knowledge in your college lectures. But our intention of this lecture is that you should be aligned with the practical aspect of the structural steel design, how to design the real world structures. So, for that, you do need to understand how the basic modeling is done, and it is much more easier to understand the structural steel design with practical building applications. So we shall be learning this in ETABS also and in space gas also. So primarily we shall be discussing about the whole lectures in ETABS, and at the end of the lecture series we shall be discussing that how we can design practical steel structures in space gas also. But first, you can open the ETAB software and then you can just click on the new model option. So here you shall get the settings that either we can have the units as metric SI, because that is the one that is available in Australia, and steel section database we can select here as, we can say, Australian, New Zealand, and after that steel design code we can select AS 4100 2020, and concrete design code we can select AS 3600 2018. So these are the settings that are available in ETABS, we can say 21 version. But before that, you might be getting AS 4100 1998 if this is a 20 version software. So 1998 and 2020, there are no as such very major revisions. There are, we can say, some the theoretical calculations and formulas that are common in both in 1998 and 2020. So we can click on as of now AS 4100 2020, and after that we can just open the this option shall come that we can adopt the uniform grid spacing and number of simple story strata. So I presume that you do have some knowledge about the modeling part in ETABS, because that I won't be discussing here, but I shall be discussing about the basics of the structural steel design. So number of stories we can select it as 1. Typical story height we can select it as, let us say, 4 meter, and bottom story height also as 4 meters. Number of grid line in X as 2 and Y also as 2, and spacing of grids in X direction as 6 and in Y direction also as 6. So after that we can left click on OK option here. So this is the screen that we shall be getting. On the left we shall be having the model explorer. So in majority of the modelers do not use this particular option. So we can just cross this option, and this is the basically the view in plan, and this is the view in 3D view. So we can just a little bit minimize it, and because we shall be primarily working in the plan view itself. But at the same time, it is better that you can left click on keep the 3D view also open, so that you can understand what exactly are you doing in this particular plan view. So after that, first option that we do need to understand are defined material properties. So we can just click here and define material properties. So in here we shall be having some, we can say, standard properties of the structural steel that shall come by default. So AS 3679.1 300 grade, thickness between 11 and 17 mm. AS 3600 2018, which recommends 40 MPa grade of concrete. AS NZS 4671 G300E, that is the one that is for the, we can say, box sections. And 4672.1 wire ordinary, that is for the post tensioning or pre-tensioning strands. So these are the 4 materials that comes by default when you click on the Australian standards. So after that we can just to explain, you can just click on this AS 3679.1 and left click on modify show material. So in here, left click again on modify show material design property data. So you shall see that 300 grade is basically the yield stress 300, and after that tensile strength is 440, expected yield stress is 345, and effective tensile strength, that is basically 506 MPa. So 300 grade steel is basically 300 yield stress of the structural steel, and thickness is usually between 11 and 17 mm. So how we can add these members? We can left click on add new material option, Australia, material type is steel. AS 3679.1 is the one that is the code for the hot rolled sections, that is universal beams, or we can say or universal columns. So after that, grade of the structural steel. So grade is basically dependent on the thickness itself. So for thickness less than 11 mm, thickness between 11 and 17, thickness greater than 17. So after that, the second option is grade 350 steel, thickness less than 11, thickness between 11 and 40, thickness greater than 40 mm. So we can select grade 300 and thickness less than 11 mm also. And for this, basically the yield stress, that is a little bit higher, that is for 300 grade, it gives us 320 Newton per mm square as the yield stress, that we have already discussed in the earlier lecture, that for thickness, lesser thickness, higher yield stress is allowed. And after that, again we left click on add new material, and for thickness greater than 17 mm, the yield stress is approximately 280 MPa. So that is the one that has been considered here, because for higher thicknesses there are these residual stresses that are there in the structural steel plates that basically forms the universal beams or universal columns. So that is why yield stress is lesser for larger thicknesses. So similarly, if required, we can add grade 350 steel also in same philosophy. For thickness less than 11 mm, it is higher than 350. For 1140, it is same. And for thickness greater than 40 mm, it is we can say lesser than 350 mm. So after that, if required, we can add this AS 1163 2016, that is for the hollow sections. So we have three options, it is C250, 350 and 450. So if we click on grade 350, basically our yield stress, that is again 350 Newton per mm square or MPa. So we can add this material also. And if required, we can have AS 36781 also 2016, that is for the plate sections. That is, let us say if we are going ahead with the built up structural steel members, that is the members in which the web and plants, they are basically made with the welding. So that is, although I think not that much common in Australia because of the higher fabrication costing involved. So that is why it is recommended that we can proceed with either 3679.1 or AS1163 for rectangular hollow sections. So these are the different types of material grades that we have selected for the structural steel members. So we can left click on OK here. After that, we have already defined the material properties. And the good thing about the ETABS is that either some of the engineers are comfortable using these toolbar options. So we can left click on options here, and we can left click on reset default toolbars if some of the toolbars are missing. But if required, we can add some toolbars also. Let us say assign joint or assign frame, assign shell, edit, view, define. So there are these many engineers who are much comfortable using the toolbar option itself. So many of the engineers, what they do is that instead of going for define and material properties option, what they do is that they just simply click on this option here, that is define material properties. Similarly, instead of adding define section properties here, what they used to do is that they just click on this option here, define frame sections. So that all depends on your we can say requirements, that, or we can say experience also, that how you need to proceed or how you want to proceed with this. So frankly, I'm much more comfortable using the text option here, and engineers that are younger than me, they are much more comfortable using these toolbar options. So being an old man, I do prefer to follow these options. So we can just left click on options, and we can say reset default toolbars. So that is just a simple clean screen. So after that, we can go to define material properties that we have checked. After that, we can go to define section properties and frame sections. In this particular option, we can left click on either add new property or import new properties. So we can left click on import new properties, and in here we can left click on steel and eye wide flange section. So in here we can left click on this Australia New Zealand option, And here, we can just see that there are these various UC also available, universal columns, universal beams are also available, and there are other members also, that is WC section, SC section. So we won't be dealing with these sections, but we shall be restricting our discussion on UB and UC because they are the one that is primarily used in Australia. So for beams, we can select 310 UB32. That is, the height of the UB is 310 approximately, but the unit weight is 32 kg per running meter. So we can left click on OK option here. Again, we can add similar kind of, we can say, I property as the universal columns. So as of now, we can select UC. Let us say we are selecting UCS 250 UC 72.9. That is, it is 250 mm in, we can say, size, and 72.9, that is approximately 73 kg per running meter. So just for discussion here, we can select these, we can say, box or tube sections also. So these are the box section or tube sections that we have already discussed in the earlier lecture. So let us say we are proceeding with 200 by 200 by this is basically steel tube. So we can proceed with 200 by 200 by 9, let us suppose. We can left click on OK option here. So now we have defined the materials also, but the only problem here is that you do need to take care of the material that you're using. Now if we are having a flange thickness at web thickness at 9 mm, this material property is wrong, that is, it is between 11 and 17. Although it is a little bit on conservative side, but you do need to understand that as if it is a box section, we do need to select AS1163C350. Assigning 3679.1 material property on a box section is wrong. So we can select a 350 grade 1163 box section. Now it is okay. After that, 250 UC 72.9. For this particular case, 250 UC 72.9, you can see that thickness of the web is approximately 8.6 mm and flange thickness, that is approximately 14 mm. So as of now, what we can do is that we can select AS3679.1, 11 and 17, because primarily, we should be dealing with the behavior as beam column members. So as the flange is approximately 14 mm, that is in between this. So that is why we can select as this particular member, that is, it is between 11 and 17 mm. Similarly for 310 UB32, we can just double click on this particular option here. So the thickness of the flange is 8 mm. Thickness of the web is 5.5. So for that, we are dealing with thickness less than 11 and 3679.1. So we have dealt with all the three material properties that needs to be assigned. For thickness less than 11, thickness between 11 and 17, thickness greater than 17 mm. So we can just left click on OK option here. So our material properties are also final. So after that, we can just left click on draw beam column brace subject, and then we can left click on draw beam column brace in plan elevation of 3D. So in here, frame, and after that we can just select here as, we can say, 310 UB32. Moment radius is continuous, that is, we are not taking it as of now as simply supported, because I just want you to understand what are the different in a simple, we can say, portal frame or a simple steel platform structure, what are the members that carry compression, what are the members that carry the bending, what are the members that carries the tension. So that is the intent of this particular lecture before we start in detail design about the different kinds of or the design of tension member, design of compression members, etc. So we can just click on this option to this option, this point to this point, this point to this point. There is a little bit of wrong modeling that I have done. What we need to do is that we first of all need to go to draw and snap options. So this is a very important point that many engineers miss. That basically leads to, we can say, orphan nodes also, or a very wrong modeling concept. So first of all, we do need to find out this point, grid point A2. Now this is okay. We start from this point up to grid point B2. So now if this is grid point B2, this is okay. But if this is the case, then we are going out of the node and this is wrong. So that is why we do need to ensure that we are modeling it correctly. So grid point B2 is okay. And after that, we find out grid point B1, that is also okay. And again, we find out, yeah, because if this is the case, 6.1, then this is wrong because our grid is of 6 meters. So we do need to find out grid point A1. And then again, we can simply close this, that is grid point A2. So now this is done. And after that, we can go to draw and beam column brace object and quick draw columns. So again, we can go to this particular option and we can select 250 UC 72.9. We can select it as continuous. And now here you can see that orientation of this is something like this. That is, it is horizontal. If required, we can select it as 90 degree. And then we can see that now the column is vertical. So we can just click on this option here, click on grid point B2, click on grid point B1 and click on grid point A1. So now you can see that now this portal has been completely, or we can say steel platform, that is now completely constructed. Second point that we do need to, understand is that as of now, we have just drawn a basic theory example. We can just click on this particular option here, that is move down in list, select all the joints. We can go to assign, joint and restraint, fixed restraint, apply and click on OK. So now we have assigned fixed support. That is, we can left click and right click here. And then you can see that it is restrained in all the directions. So now we have applied the supports also. Now we can go to the define load pattern. So by default, dead load and live load options always come. And just to understand the basic behavior, what we can do is that we can assign a UDL, uniformly distributed load, on all of these members. So we can go to assign frame loads and distributed, add let us say 2 kN per meter of UDL on all the beams. So now we can see that 2 kN per meter UDL is applied on all the steel beams. Second point that we do need to understand, this is to understand the bending behavior. After that, we do need to understand the, we can say, bending behavior in the columns. So what we can do is that we can go to assign joint load force. And we can go to this point here and apply 10 kN of point load. So if we select this particular point here you can see that only this node is selected. This node is not selected. So we can apply 10 kN of horizontal force on all of these nodes. So this is also, understood. So here you can see that 10 kN of force is applied on all the nodes. So let us just, go to define load combinations, and then we can click on add default design combos. We can go to steel frame design, convert user combination, editable. So these are basically the D1 and D2. These are the serviceability load combination. That's one time dead load plus live load. And this is only one time dead load. Similarly, this is the one that is strength design. 1.35 time dead load or 1.2 times dead load plus 1.5 times live load. So these are the values that are considered from the code, that is AS4100. This is also clear. So after that, you can just left click on run analysis option. So after the analysis, we can see that there is this lateral deflection of approximately 9.56 mm on the top because we have applied a very high value of the lateral load. Now the intention was to understand or to explain how the forces behave in a structural steel members. So we can go to display force stress diagram or frame pier spandrel link forces. So for the case, what we can do is that we can first of all see how the actual forces travel. So first of all, this is the standard diagram, that is, it is approximately 21, and in here it is approximately, we can say 11 kN, 10.93 approximately, that is the value of the axial load. So here also you can see that this is approximately 10 kN of the actual force, and this is approximately 20. Why? Because we have applied a large amount of the horizontal load here. After that, if you're talking about the shear, now that is also very simple, we can say, diagram. And this is the shear force diagram that we already studied in our college lecture, that shear is maximum at the supporting point and 0 at the center point. And after that, shear 33 is the shear along the, we can say, other axis. So that is not found in the steel beams, but obviously it is there when we're talking about the steel columns. Moment 33 is also very important to understand. Moment 33 is basically the bending moment about the major axis. So here also you can see that how the bending is coming for all the members here. Now there is this one important concept that when we're talking about the fixing of the steel beams on the steel columns, only one frame or only one side, that is, we can say, released, and the other one is pinned. Let me just explain to you in simple words. Now what basically happens is that, in simple words, flange is the one that can resist the bending moment. Web cannot resist the bending moment. So what we need to do is that we do need to select both of these steel beams, and we do need to assign frame, releases and partial fixity, and then we can select torsion moment M33 minor 33 and this point. So this is basically the starting point, ending point, and one side we are releasing a torsion also. So we do need to left click on apply here. So now if the beam is connected to the steel web, it has to be released. But if a steel beam is connected on the, we can say, flange, it should not be released because the flange can resist the bending moment. Let me just draw this in the simple diagram again. That two types of steel beams are there. One is that we have to, we can release on both the ends, and the bending moment diagram is something like this. Second is that the beam is something like this. So the bending moment diagram is something like this. So when we are connecting the steel beam with the flange, we have to ensure that this is a fixed connection. And if the steel beam is connected here with the web, that is basically the pinned connection. So that is the basic, understanding before we proceed further. So that is why I have released this particular steel beam. I think I have accidentally applied release here also. So we can just click on assign frame, releases, partial fixity, and then no releases and apply. Yeah, so now it is gone. So though we do need to ensure that releases are applied correctly, and releases are the most important parameter when we're talking about the structural steel design, because it can simply alter the behavior of the complete structure if applied correctly or incorrectly. So we can run the analysis again. We're going to display force stress diagram and frame pier spandrel link forces. We can click on moment 33, and then we can just click on apply. So here we can see that how it was released. So it is just a simple bending moment diagram for a simply supported beam with bending moment value as approximately WL square by 8, and here it was fixed on the column, we can say, steel column flange. So that is why it is showing the fixed behavior. And after that, this is also the typical behavior for the column being fixed at the bottom, and we can say connected with the two portal beams on the top face. So after that, this is the basic philosophy. So in here, this is the bending member, this is the bending member, this is also the bending moment, this is also the bending member. This is not a pure compression member, but a beam column member. That is, we can see a bending moment also, and we can see the axial forces also. So we have to design it as the beam column, and we have to design it as a, we can say, steel, we can say, beams or bending behavior. After that, we can just design them also. So we can go to steel frame design and view revise preference. We do need to ensure that AS4100 2020 is there. Steel type is basically the hot rolled section, and then we can just select the, we can say, design combinations also. So this is the strength combination, and these are the serviceability load combination. So they are selected correctly, and then we can just left click on this option here. So in here we can see that utilization ratio is very less because the loads are also, we can say, very less, and the ratio is very like 0.159. So we shall be discussing about this when we're dealing with the design, but just to give you a brief idea that how it is done. So after that, if we are talking about this particular member, so in here the axial forces, and we can see there is the major contribution of bending moment of the minor axis. So here you can see it is 0.439. For major it is only 0.013, because what we have done is that we have applied a 10 kN point force along this particular axis. So what I'm trying to convey is that either we can have 0.439 and design the steel beam accordingly, or what we can do to, we can say, reduce this minor moment utilization, or as a good engineering practice also, we can go to the define material properties, and we can select define section properties and frame sections. So here we can select on import new properties, and then we can select channel sections. So let us say we can select 275 by 5 and steel channel, and 200 by 75 by 5 the thickness that we can check later on. So we can left click on modify show property, and here we can see that the thickness of this particular member is only, we can say, web thickness, flange thickness is 4.7 mm. So we can select here as thickness less than 11 mm and left click on OK option here, and then again left click on OK. So we can go to draw beam column brace, and then again draw beam column brace in plan elevation or 3D. So here we can select the parallel flange channel, that is 200 by 75 by 5 cc. And after that, what we can do is that we can open the elevation along grid 1. And then here also. Yeah, so now it is okay, and then after that we can open the elevation along grid 2 also. We can check this model in the 3D view. So now we can see that we have provided cross bracing on both the side, and then we can see that whether the bending moment utilization on the minor axis that was so high. So as per the structural steel load philosophy, if we are applying 10 kN force here, that they shall simply transfer to the ground here. It won't be getting balanced by this particular steel column. So that is the advantage of the bracing. So here we can see that initially the lateral deflection was very high, that is approximately 9 mm. But after applying the bracing, here you can see the lateral deflection is only 0.326 mm, which is negligible. So that is how the bracing arrangement helps in managing the drift when we're talking about the very tall steel industrial buildings. So after that, if we want to see the force stress diagram for, we can say, frame spandrel link forces. So in here, if we are talking about the axial forces, under the axial forces, you can see that this member color is different as compared to this member, because all of these members are compression member. Red denotes compression and yellow denotes tension. So here also you can see that basically the symbol is also different. That is, in here we're talking about -13, but in here we are talking about the +11. So this member is taking up the tension, and this member, that is basically taking up the compression. So this is a compression member, pure compression member. This won't be taking any kind of, we can say, bending. And this is the pure, we can say, a tension member, and this is basically the beam column, and this is again the bending member. So we can again go to the, we can say, steel frame design option. So in here you can see that we can see the utilization ratio again here. So earlier the bending moment minor utilization, that was as high as 0.439, but in here now it is 0.004. So that is how we can say control the bending moment along the minor axis by providing the any kind of bracing structural arrangement. So we can say that for steel structures, bracing is the most important thing that we do need to assign in the structural steel buildings. If you're having any kind of structure which is a steel structure which is not having any kind of bracing arrangement, then it shall definitely have a very high value of drift, and it is never recommended to construct those kind of steel buildings. So in our further lectures we shall be discussing about a tension member. So in your mind you should be having this particular frame model that just a minute, we can left click on Control W, and then we can just left click on extrude frames option here. So you do need to understand that when we're talking about the tension members in the further lecture, we shall discussing about this member here, which is having a large value of tension. If you're talking about the pure compression member, we're talking about this particular member. If you're talking about the bending members, we are talking about this member. And if you're talking about the beam column members, we are talking about this particular member here. So this is how you can design or we can say control the modeling parameters. So don't worry, this is just a very beginning or a basic lecture, but this lecture is also very important to understand how the steel forces flow in any kind of steel structure. So in the next lecture we shall be discussing about a design of the tension members.